Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 5.1. It's titled An Introduction to Boolean Algebra. This whole chapter, Chapter 5, we're covering 3 sections on this topic of Boolean Algebra. And you're going to see it's very similar to what we saw back in Chapter 1 involving propositions, truth and false, truth values and truth tables and laws of propositional logic. There's going to be stuff that's very similar to that in this chapter. We've also seen the same laws in the chapter about sets. Right? There was De Morgan's laws and the complement laws and absorption laws and lots of stuff that repeated itself when it came to set and set operations. So this is going to seem very repetitive. Right? It's just the same topic, really packaged differently. Right. So let me show you what I'm talking about. All right. So Boolean algebra is a set of rules and operations for working with variables whose values are either 0 or 1. And that's it. You're only going to see zeros or ones. Now, we're going to basically equate 0 to being false, like corresponding to false, and the number 1 will have, it'll correspond to like true, back when we were talking about propositions and truth values. As they're saying here, the rules for Boolean algebra will seem very familiar if you have studied propositional logic, right, back in Chapter 1. In fact, the definitions of Boolean operations are basically a restatement of logical operations with slightly different notation. Right? So it's the same stuff, just with a different package, in a different packaging. Right? So the value 1 will correspond to like a truth value of true in the rules of propositional logic. And the value 0 will correspond to a truth value of false. Okay? Alright, so we have a few operations to go over. There's Boolean multiplication, Boolean addition, and complements, almost like Boolean negation. So Boolean multiplication, denoted by like a little multiplication symbol, a little dot, applies to two elements, from the set 0 and 1. Again, everything you deal with in this chapter will involve the number 0 or the number 1, and that's it. And obeys the standard rules for multiplication. So the results of multiplication operation are the same as the logical AND operation. Remember conjunctions? And. So they put them side by side here. Remember, a false statement and a false statement was a false statement. A false statement and a true statement was a false statement. A true statement and a false statement was a false statement. The only time a conjunction ended up being true was when both individual propositions that made up the conjunction were true. True and true was true. Well, if you just replace all these falses with zeros and all the trues with ones and all the and symbols, the conjunction symbols with the multiplication symbols, you get exactly the same thing. So in Boolean multiplication, 0 times 0 is 0. Again, that's just like false and false is false. 0 times 1 is 0. Again, that's just like false and true is false. 1 times 0 is 0. That's just like true and false is false, and 1 times 1 is 1. Just like true and true is true. You're back in logical propositions studies, right? And as they mentioned up here, this works exactly like you would expect it to when you multiply numbers, right? See, anything times 0 is 0, and 1 times 1 is 1. So Boolean multiplication works out in a nice way. Alright, so if Boolean multiplication is like the AND operation, right, conjunctions, we're going to see that Boolean addition is like that inclusive OR operation, right, for propositions, the disjunctions. So Boolean addition, which, just like addition normally, denoted by a plus sign, applies to two elements, 0 or 1, and obeys the standard rules for addition, except for 1 plus 1. Right, so this is where it's going to get a little tricky. Remember, the only numbers that are going to show up are 0 and 1. So here in Boolean addition, 1 plus 1 is not 2. Okay, we're going to see that 1 plus 1 is 1. And again, think about it as true or true with the inclusive OR. So an outcome of 2 would not be allowed, as I mentioned, right? Because all values in Boolean algebra must be 0 or 1. So the results of the addition operation are the same as I mentioned already, the logical operation OR, right? The inclusive OR, the disjunction. So again, they have these side by side. So if you refresh your memory here, the logical operation, the disjunction, the inclusive OR, false or false was false. False or true was true. True or false was true, and true or true was true. Now just go through your logical operation here. Replace all the falses with zeros, all the trues with ones, and all the OR operations with addition. And you get the same stuff in this Boolean addition. Right. So 0 plus 0 is 0, like normal, right? 0 plus 1 is 1, like normal. 1 plus 0 is 1, just like normal. But here's again where the people tend to trip up. 1 plus 1 is not 2 in Boolean algebra. 1 plus 1 is 1. And again, that's just like true or true is true. Okay? Alright, and then finally, the last of these three operations, these Boolean operations we're going to study, the complement. Just like the not, and you saw a complement of a set, right? Just something that's not in that set, very similar. So this is like negation. And it's going to be denoted with a little bar symbol above an expression. So you see 0 with a bar over it here, 1 with a bar over it. It's just like the not operation, the negation in logic. So not false is true, not true is false, right? So the complement of 0 is 1, the complement of 1 is 0. Very, very simple. All right. And then they go through some examples. They have again. If you can refer back to these tables up here, but should be pretty simple. Again, if you think of ones as true statements, zeros as false statements, multiplication as the AND operation, the conjunction, addition as the OR, the inclusive OR, the disjunction, and the bars, right, the complements as not, or negations. So this is 1 times 0. True and false was false, right? And Again, everything really works out the same way that you would expect in arithmetic, except for 1 plus 1. Right. 1 times 1, 1. 1 plus 0, 1. 1 plus 1 is not 2, it's 1, remember? And then the negation of 1 is 0. Right? The complement of 1 is 0. Easy stuff. Now, Claude Shannon equated this to circuit switching. So these are just pictures to represent different operations. So imagine, this little picture here is a battery producing charge. And you're trying to light the light bulb, and the light bulb will only light if there is a closed path, a loop that takes electricity through to the light bulb and then back to the battery and all that. So this picture on the left is equivalent to x and y, or x times y, because both the switches for x and y need to be closed in order for the light bulb to light. And she considered closed, or Shannon considered closed to be 1 and open to be 0. I'm sorry, it was Claude. I said Shannon, that's why I said her. It's Claude Shannon. Right? Yeah, so see, 0 times 0 would be equal to 0, and then the light bulb being on is 1, and the light bulb being off is a 0. So you see here, I'd have 0 times 0 is 0. And if they were both closed, it'd be 1 times 1 equals 1. Right? Because if they were both closed, the light bulb would be turned on. And if one of them was closed and the other one wasn't, it'd be 1 times 0, or 0 times 1 would be 0. The light bulb would be off. And then this picture here would represent x or y, or x plus y. Right? Because if x was closed, you'd be able to find a loop through to the light bulb. Right? Just follow the x path. If y were closed, you could follow the y path and get a loop and turn the light bulb on. So you could have 1 plus 0 on closed switch, open switch, and the light bulb would be on. So 1 plus 0 would be 1, or 0 plus 1 would be 1. And if they were both closed, 1 plus 1 would be 1. The light bulb would definitely be on. And in this case, these 0 plus 0, when they're both open, the light bulb would be off, right? 0 plus 0 would be 0. Okay. Yeah, so and then, playing around with these pictures, you could show when two particular operations were equivalent. So like this here would be saying that x times y plus x times z, right? This is x and y, or x and z, would give me the same results. The light bulb would be on in the same situations as in this picture if you just had x times the quantity y plus z. Right? Putting these pictures together. Right? So again, what this is saying is the following, that it's saying this. And this is actually a property we'll see later. It's saying that x times y, or right, plus x times z, x and z, is equivalent, has the same output in Boolean algebra as x times the quantity y plus z. And this is actually the distributive law. You can distribute multiplication over addition. X times y plus z in Boolean is equivalent to x times y plus x times z. So I'll even write that over here. This is a distributive law in Boolean algebra. Okay. Now there is another one. we'll see later that x plus y times z, right? And if you want to put parentheses around the y times z, that's fine. This works like, this first distributive law works the way you normally remember, right? If you have a multiplication over an addition, you can distribute. But in Boolean algebra, it also works the other way. You can distribute addition over multiplication. So x plus y times z in Boolean is equivalent to x plus y times x plus z. I put the x plus on the y, then times, and then the x plus on the z. Alright, it's really weird, but so these are both what are called the distributive laws. And you've seen these, right? You've seen these. You've seen these in propositional logic with ands and ors. You've seen these in sets, right? We're talking about set notation, sets with unions and intersections. You've seen these, right? It just looks weirder with the addition and multiplication because of how you were raised in regular algebra class. All right, but this is Boolean algebra, so things are going to be a little different. But if you remember your propositional logic and your set stuff, this should be exactly the same. All right, we'll talk about showing that two expressions are equivalent later in this section. All right, so variables that can have a value of 1 or 0 are called Boolean variables. Boolean expressions can be built up by applying Boolean operations to Boolean variables, or the constants 1 or 0. The value of a Boolean expression with multiple operations can depend on the order in which the operations are applied. Alright, so here's the order of operations, the precedence rules for Boolean operations. So as usual, you do multiplication, right? You do your ands before the ors, right? You do multiplication before addition. The complement operation, right, that bar, is applied as soon as the entire expression under the bar is evaluated. And of course, parentheses always take precedence. Parentheses can be used to override these rules, right? So if you see an expression in parentheses, evaluate that first. Okay, so now we go through an example. So I'll write these out. You can watch the animation as well, but I'll do it on paper, evaluating these Boolean expressions. Alright, so here's the first expression in that animation. It's you got your Boolean variables, x, y, and z. They can take on the value of 0 or 1. And then all this put together is a Boolean expression made up of Boolean variables and operations, and the number 1 or 0 might also pop in there. Now it's just like any other function, just like any other expression. I'm asked to evaluate, find the value of this expression if x and y and z all have the value of 1. So I just substitute those. So you have 1 for x times, if they're next, again, if they're next to each other, touching, that's multiplication, just like in algebra class. Right? So I have 1 times 1 plus 1 times, the complement of 1, right? Again, just replacing the x and y and z with the number 1. Alright, so this complement I'm going to do first because it says, remember, it says you're going to apply the complement as soon as the expression underneath has a value, is evaluated, which it is. I know that this is 1, so I'm going to apply as soon as I know the expression underneath the bar is 0 or 1, I'm going to apply the complement. Alright, so this is 1 times 1 plus 1 times, and then the complement of 1 is 0. Right. Then you do your multiplications, right, before your additions. So I'm going to do the 1 times 1 and the 1 times 0. Do those first. All right, so 1 times 1, remember, is 1. And you got the plus here. 1 times 0 is 0. And then finally the addition. All right, that's the only operation left. 1 plus 0 is 1. Right? So the value of this expression, when the Boolean variables take on the value of 1, is 1 itself. Okay, so simple enough. Then they have another one. Okay, here's the second Boolean expression thrown at me in this participation activity. As to again evaluate it, is it going to be 0 or 1? And yeah, I know you could guess, you'd have a 50-50 chance, but let's try to practice this stuff. Okay. All right. So the values of the Boolean variables here are, x is 0, so I've got 0 here, plus, the value of z is 1, times, and then notice here I got a big bar over this expression in parentheses, right? So I'm going to evaluate the expression in parentheses first, and then once that's done, I'll apply the bar, I'll apply the complement. So I've got 0 plus, y. The value of y is also 1. Alright, so first, the expression underneath the bar, right? The expression in parentheses here. So this is 0 plus 1 times, and then in parentheses, 0 plus 1 is 1. So I got 1 here, but then again the bar above it, right? I'm doing the complement. And as mentioned earlier, as soon as you evaluate the expression under a bar, apply the bar, apply the complement. So I'm going to do this complement next. So I have 0 plus 1 times, and then the complement of 1 is 0. Alright, then, the multiplications before the additions. So I'm doing this 1 times 0 first. So I have the 0 out front first still, and then plus, and then 1 times 0 is 0. And then finally, the only other operation left is the addition, right? 0 plus 0 is 0. Okay, so the value of this expression, when the values of the Boolean variables are these, 0 for x and 1 for y and z, the value of this expression is 0. Alright, like I said, you can look at that here, play the animation, watch what they're doing the exact same stuff that I did. Alright, then you're asked to do the same here. So I'll just kind of talk the first couple here out loud, and I'll leave the rest to you. There's only 4 of them. So here I'll just do the first one. Alright, these aren't terrible. Write them out. Make sure you know the order that things are coming in, right? The order of the operations. So I have x plus, the complement of y. See, the bar is over the y. And then that's in parentheses, and then you're getting times z. Now let's see, x is 0, y is 1. So in the parentheses here, I'd have 0 plus 1 complement. Now the complement of 1 is 0, so you have 0 plus 0 in here, which is 0. And then 0 times 1, right, 1 for z, 0 times 1 is 0. Okay? And like I said, I'll leave the rest to you. They're not too bad. And then you got 7 of these in your challenge activity. So they tell you the values of the variables, and then they give you an expression. And your answer is going to be basically just 0 or 1. So let's see, that first level is a pretty basic one. The second level, again, every single one of these is the same. Evaluating some expression when you know the values of the variables. And they get a little more complicated. Here the bar is over x plus y. So you do x plus y first, and then apply the bar, apply the complement. Pay attention to parentheses, where the complement bars are. Yeah, so they're all the same, right? They just get a little more complicated as you go through the levels, but your answer should be either 0 or 1. All right, now I mentioned this earlier, when I talked about the distributive properties, the distributive laws. Two Boolean expressions are equivalent if they have the same value for every possible combination of values assigned to the variables, right? So they have the same value, they're equal all the time, no matter what you plug in. For example, right, the expressions x plus y and x y bar, x times y bar, these are not equivalent, right? Not equivalent, because when x and y are both 1, x plus y is equal to 1, but x times y bar would be equal to 0. So they don't have the same output for any input, right? They don't have the same output all the time. Now remember in propositional logic, remember back in chapter 1, the symbol with the triple equal sign meant that two expressions were logically equivalent, right? Two statements were logically equivalent, had the same truth value all the time. Well, in Boolean algebra, it's just the equal sign again. The equal sign is used to denote logical equivalence, or equivalence of two Boolean expressions. And hey, look at these laws of Boolean algebra and tell me you haven't seen these before. If you say that, you're lying. Alright, you have seen these before, but they were in propositional logic and also for sets. So I am not going to go through these. I'm not going to read these off. You've seen them, but with unions and intersections and sets. You've seen them with ands and ors, conjunctions and disjunctions in propositional logic and negations. You've seen all of these, and they have the same names, right? The idempotent laws, the associative laws, commutative, distributive. And I've shown you the distributive. I've already written the distributive out. Identity laws. Again, if you replace all the pluses with ors, all the multiplications with ands, all the ones with true, all the zeros with falses, and all the bars with negations, you get the exact same stuff as in chapter 1. All the same laws. Right. So as in chapter 1, we're going to be using these laws to prove that certain expressions are equal. Right? So these are always true. Right? You should know that. These are always true. X plus x will always have the same value as just x. Right? X plus 0 will be equivalent to x. The complement of x is x, and so on. Right? All these are always true, and we're going to use these to show that other expressions are always equal as well. And it's just like back in chapter 1, or in the chapter on sets as well, chapter 3. So I'll show you I'll show you here, this participation activity on paper. Okay, so we're going to use our laws of Boolean algebra to show that this crazy expression, x times y plus, not x times y, or the complement of x times y, plus, z times y, to show that this expression will always have the same truth value or Boolean value as just y. Right. So remember how this kind of works. Hopefully this looks familiar. Right. So I'm going to start with one side. Now usually it would be easiest to start with the side that looks most complicated. So that's clearly this left expression. So I start with x times y plus, the complement of x times y plus, z times y. And then I'm going to go through one step at a time and apply different laws. So now these first two terms both have this y in common. So you can kind of like factor that out, the distributive law. So this is equivalent to x plus the complement of x, right, just these two here, times y. Now I know all three of them have y, so we'll eventually pull it out of all three, but just take two at a time, right? Because again, the distributive law technically applies to two terms at a time. All right, then plus z times y. And then off to the side, and you've done this before, state the law that you just used. How can I say that this is equal to this? It's because of one of those distributive laws. All right, and I'll just write the word distributive next time instead of the word law. All right, and then something else I noticed. Now you could pull out the y from both of these now if you wanted. But one thing I'm noticing is this here. X plus the complement of x. Now do you remember that a set, in union with the complement of that set was the entire universal set, or was always true, or remember with ors, a or not a was true all the time. So x plus not x is always 1, right? It's always true. So x plus not x, x plus this is 1. So I have 1 times y plus z times y. And the reason I can say that, that was one of those complement laws, that x plus the complement of x is 1 all the time. Okay, and now I'll apply the distributive property again. Distributive law, see again both of these have this times y in it, have this y term, so pull that out. This is 1 plus z times y, and again I applied the distributive law. All right, and now 1 plus z, well, anything plus 1 is going to be 1, right? It's like anything or a true statement will always be true. Okay, and this was, a domination law, one of those domination laws. So anything plus 1 is 1. And this was, like 1 dominates an addition, 0 dominates a multiplication, right? Anything times 0 is 0. So this is one of those domination laws. And then finally, anything times 1 is itself, and we get, I want to end with this right side. I start with the left side here, and I use laws to show that yes, indeed, this expression is equivalent to this one on the other side, and you see I'm ending with that here. And the reason I can say this is, again, that was one of those identity laws, or anything times 1 is itself. And then I guess I'll put a little it's technically a proof. Right? You put a little box at the end. You have shown, you have proven that one expression is equivalent to another. So no matter what you plugged in for x, y, and z, the output will be just the same as what you plugged in for y. Right? So if I put in 0 for x, 1 for y, and 1 for z, the output will be 1. It's just whatever I plugged in for y. These will always have the same value. All right, so hopefully that looks familiar, right? This concept of starting with one expression or one set, showing that it's equal to another set using the laws, or starting with one statement, one proposition, showing that it's logically equivalent to another proposition using laws. It's exactly the same stuff. All right, you just have to know the laws. And they're the same. They're the same as before. Okay, so you're asked to kind of do that again down here, where you match each Boolean expression with an equivalent Boolean expression. Now, do they have De Morgans? Yeah, they do have De Morgan's. Okay. It's like they should be the same. All right. So I'll just kind of speak one out loud here. Like this first one. When you have a complement of a sum, that's equivalent to the product of the complements, right? That's De Morgan's law. So when you have x plus y with a bar over it, that's equivalent to x bar times y bar. So this first guy here. And then you see how the second part, z plus not x, is exactly the same. So this one is equivalent to, this one here because of De Morgan's laws. All right, and I'll leave the other two to you. And then they got a word about Boolean, and again, they're just reminding you that multiplication is like intersections in sets, additions like unions, right? Because earlier they said this was like propositional logic, and now they're saying, hey, remember sets as well? All this stuff is coming back. It's very similar. And then you have your additional exercises. All right. So again, some of these are assigned. Some of them are, some of these are in assignment 6. Some of them might not be. I would still recommend that you try them all, just to get more practice, get more familiar with the material. You do have the solutions that you can view to check how you're doing, and please only use them to check how you're doing. Don't just copy the solutions down. You're not going to learn anything that way. Try to work out the problems, try to figure them out before you look at the solutions. All right, you'll learn a lot more that way. All right, and in fact, I think all of these might be on assignment 6, but still, I would recommend you try them all. All right, so that's it for the introduction to this Boolean algebra. Hopefully, this video is a nice guide for you. And if you have any questions, let me know, of course. And thank you very much for watching.